geometry. So in a n of k, an algebraic set is V of f1 up to fn in ank. Right. So this means the set of tuples. So a guy in here is called P, a1 up to an. It's a set of P such that fi of P equals 0 for all I. Right. So I give myself some polynomials. So here's f1 equals 0, and here's f2 equals 0, and maybe some whatever's left when you set all of those equal 0. So there's a problem here, which is that this is just a definition. And there's no guarantee that it's sensible, and it may be not sensible. So, e.g., if f1, if k is the real numbers, and f1 is for example x1 squared plus 1, then you can guarantee, without looking at a2 up to an, and without looking at f2 up to fn, then you're going to then v of f1 up to fn, fm is guaranteed to be empty, right? And whatever n and whatever f2 up to fm are. Right? So this is just a warning. At the moment, I'm going to do formal definitions, very formal manipulations, but the upshot in next time's lectures, the upshot was it really only works. It really only makes sense. Only makes sense if K is algebraically closed. So, e.g., K equals the complex numbers. So if K is the complex numbers, then I write this down, and it's just two planes. It's x equals plus I and x equals minus I. That's two planes, and then all of the rest of the equations make sense in those two planes. Right. So this is just a warning. I can make this definition if I want to. Right, and the fact it's not sensible is just a secondary matter. Okay, so the same definition. If I in A is an ideal, I can write down V of I in AN, and I can define this to be the set of points P such that f of P equals 0 for all f in I. Right? So these two definitions are exactly the same, because given I, so because given I, I can write I equals f1 up to fn, so fm for some fi, and then v of I is just v of f1 up to fm. Right. So if these generating guys vanish at a point, then all their linear combinations vanish. So also everything in I vanishes, and conversely, if everything in I, so so this is the definition of an algebraic set. So algebraic sets algebraic sets V. So, you know, this is the same thing as a variety, but later on I want to be just a little bit more precise. So I'm going to continue calling this an algebraic set for a while. So a variety will be an algebraic set, and an algebraic set will be a variety. So it's the same, they're the same thing, but there'll be a little bit of extra precision when I... Okay, so an algebraic set V in A, N, K. So they have the following property. These are trivial properties. They have the following properties. Right, so, you know, just to tell you about the empty set is an algebraic set, algebraic variety, and also the whole of space is an algebraic sets. Okay, so you know, this one is true because if I set 1 equals 0, it's a certain polynomial, and 1 equals 0 is satisfied by all the elements of the empty set. Right? Whereas if I set 0 equals 0, then it's no condition at all. This is just trivial. This is just stupid nonsense you say at the beginning. So then I want this thing that if V1 and V2 are algebraic sets, then V1 union V2 is a game. Right? Or more generally, union I equals 1 to n of Vi is an algebraic set. If V1 Vn are. Yes? And then if V lambda in lambda is a set, is any collection of algebraic sets indexed by lambda, then the intersection of all the V lambda is again an algebraic set. Right, and so you know, what are we doing here? So this guy here is if V1 is V of I1, and V2 is V of I2, then V1 union V2 is V of I1 intersect I2. Okay, and that's the same thing as V of I1 times I2. Okay, so you know, these are trivial things, but we still have to think about why they're true. So if I take the statement is if I take a point which is either in V1 or in V2, then everything in this intersection vanishes on it. So if my point is in V1, then already everything here vanishes on it, and so certainly everything in the intersection vanishes. And you know, this I1 times I2 is certainly contained in I1 intersect I2, and so the thing I just proved, if you think about it, says that. Okay, so the other way around, what does it mean? So suppose I take a point P, which is not in either of these. So if P is not in V1 and not in V2, this means that there's some F in I1 and some G in I2 with F times F of P not equal to 0, and G of P is not equal to 0, and therefore F G of P is not equal to 0. Right? And therefore, if I take a point which is not there, then it's not there either. And so this proves that way. Right? And so therefore equals. Okay, and this one, why do I need all this infinite notation? Why do I need this notation of infinite sets? So V lambda, if V lambda algebraic set means that V lambda is V of I lambda, some ideal I lambda. Okay, so what does it mean to say that P is in intersection of V lambda? Right, so this is the intersection of V of I lambda. So this means this guy P is a point of space. It's one of these points A1 up to AN. P is A1 up to AN. And this means it satisfies all the conditions here. So this means that all the F in I lambda, for all lambda, satisfy F of P equals 0. Right? So in other words, in order that P should be in this intersection, it means that P should satisfy the conditions defining V of I lambda for each lambda. Right? And that means that all of these F's are supposed to vanish there. And this means that if and only if P is in V of the sum of I lambda. Right, so I have a whole pile of ideals here, probably infinite, possibly infinitely many of them. And I say that, I'm writing down possibly infinitely many conditions on P. This P should have all of these polynomials for possibly infinitely many values of lambda, and they should all vanish. And that's just the same saying that P is in the variety of, it's a place where all of these guys vanish. Right? So, however, it so happens that this is I is sum of I lambda is an ideal of A. And so therefore it's of the form, G1 up to Gm, the sum Gi. Right? And so actually this is if and only if P is in this V of I. Right? And this is just one of these algebraic sets. Okay? So, I've done this very formally. I've written out these properties. So this says that, so therefore, the algebraic sets, algebraic subsets, algebraic sets in AN of K form the closed sets of a topology. Okay, so the people who've not seen the definition of topological space before. So, as you all know, topology is taught in analysis. It's a branch of analysis. So, topological space, topology T on set X is a set of open sets. Right. And they satisfy the complement of these two properties. So they satisfy that the empty set is and the whole set are both, and then a finite intersection or an arbitrary union. So just take the complement of the statements here. Right. So this is used for kind of epsilon delta calculus, or at least the continuity part. Right. However, in algebraic geometry, it's used in really a much, much simpler context. Right, so this topology is called the Zariski topology. So Zariski was a Russian Jewish mathematician who studied in Italy in the 1920s and 1930s, and then went to America and became a professor at Harvard. So he taught people like Mumford and Hironaka and implicitly me. Right. So let me say, you're used to this topological space where you sort of draw pictures like this, and here's an open set. And so on. And this is really not what the Zariski topology looks like. So this is NB. The Zariski topology is very weak. Right? What it means is that so, for example, if f, well, we're going to see lots of examples of what I mean here, but let's do some examples. E.g., in A1 of K, or in any one-dimensional variety. So I haven't defined variety, this doesn't really make sense, but just think about A1 of K. Then a closed set is either the whole of A1K or it's finite. Okay, because. So, we're talking here about polynomials in one variable, k of x, right? And the variety of f is a set of x. So x is in A1. It's just one value in A1 of k, such that f of k x equals 0. Right? So this is a polynomial. And so it has degree some n, and so this is less than or equal to n points. Yes? So, students starting algebraic geometry is probably used to working with the complex numbers or the real numbers and thinks of them as having their complex or their real topology, which is really this epsilon delta closeness. Right? And that's really nothing to do with the Zariski topology. So the Zariski topology, if I say that some set is closed in the Zariski topology, it means that there are polynomials, there's a set of polynomials that vanish on it. Right? So this was an example, e.g., and this is a harder example, so in A2 of k, so this is the xy plane, right? A Zariski closed set is a union, a finite union. Well, it's okay. Either the whole of A2 or a finite union of curves and points, of curves and points. Right, so I'm not going to prove this completely here, but I'm going to give some indications, and I'll set it as part of the homework. So what I'm doing here is I'm going to write down some polynomials and say I want those polynomials to be 0. So one possibility is that I write down no polynomials at all. So then I'm not imposing any conditions at all, and I get the whole of A2. The other possibility is that I write down at least one polynomial. So if I write down a non-zero polynomial, I'm going to get f equals 0. That's already cut down my variety to a curve, or possibly a union of curves if my f was reducible. Right? And then if I write down some other g, then I'm getting a finite set. Right? So I'm getting a finite union of irreducible curves and finite number of points. So, you know, maybe, so here I've written down f equals g equals 0. So if there's only one f, then, you know, the f possibly breaks up. It's a union of irreducible curves. And then somewhere, it's possible that somewhere there are also some finite number of points. So this is very small. These topologies, if we run over the reals, then this is, this is a closed, nowhere dense set. The complement of the set is real open and is real everywhere dense. Right? And it also has this characteristic finiteness property. Right? So we'll come back to this again. This is, you know, this, for example, if I tell you I'm going to take one of these algebraic sets, and then inside it I'm going to take a strictly smaller algebraic set. That means in each of these curves, either I'm going to throw away one component to get a smaller set, or I'm going to cut the curve by another hypersurface to get a finite set of points in it. And so this means that I'll say this in more precisely later and more generally later, but what you're getting here is the set of closed sets has the descending chain property. If I take a variety and then I take a smaller variety and I take a smaller variety, then if I have a descending chain, that can only happen finitely many times. Right? So we'll have that, we'll come to that later. Okay? So this is not really a topology in the sense of analysis. It's just this kind of convenient algebraic language. Okay, so what else am I supposed to be telling you about this? So what comes next? Okay, so I've done the so I have to I don't think there's anything else to be said about in other words, I've told you how to go forwards from I, an ideal, goes forwards to V of I. This is an algebraic set in AN. Right. Now, eventually, we're going to be able to make an inverse of this map. Maybe it's just cleaner if I call this J here. Right. And so I want to go from a set X in AN K. I want to go back to an ideal I of X, an ideal in K of X1 up to Xn. Right? And so eventually I want to put these together to get a, you know, the statement of the Nullstellensatz. So yes. So what I'm doing here is it's basically the same. It's one of these expressions. So let X be any subset of ANK. Right. Then I define I of X to be just a sort of opposite of it's a set of F in K of X1 up to Xn such that F of P is 0 for all P in X. Yes. So, you know, I hope that you know, the idea that the aim of making these two correspondences, doing this V thing, going from an ideal to an algebraic variety, and doing this I thing, going from a set, going back to an ideal, you know, there's a kind of aim that eventually we'll be able to make these inverses of one another, right? But they're certainly not inverses of one another without any further assumptions, without any further conditions. Right. So again, we do some formal. We can do formal properties of this. I'm not quite sure how interesting it is, but right. So if I start with J, and I go forwards to V of J, right. So and then if I take V of J to be my X there, V of J, and I apply I to it, then this is an ideal, and in the same ring, K of X1 up to Xn. Right, and certainly J is contained in this I of V of J. Yes, because V of J is a set of places where J vanishes, and I is a set of polynomials that vanish on that set. So certainly the element J vanish there. Right? But in general it can happen, in general this one can be bigger. Okay? So when is it, and you know, I can say the same thing here. I can go start with a set in AN, take it forwards to I of X. Take it backwards to get this ideal, the set of polynomials that vanish on that ideal. And then I take it forwards again. So by doing, so I'm just going to say exactly the opposite now. I'm just going to say the exactly the converse construction to this. So if I start with X in AN, any set, I get I of X. So this is the ideal, and then, so this is an ideal. Yes, okay, so why, I mean, this is an ideal for the obvious reason that if F and G both vanish on X, then any linear combination of F and G with coefficients in the ring. So, because if F and G are identically 0 on X, then also also AF plus BG is identically 0 on X. Right, so I can do these ideal combinations of F and G, you know, for nothing. It's free. Okay, so this is an ideal, so I can do V of I of X. Right, and whatever else this is, this certainly contains X. Right, so because, you know, the ideal of this I of X is the set of polynomials that vanish on X, and then I do V of that, so I take the set of points where all of those polynomials vanish, so that certainly includes X, right? But it might be much more, right? But it can perfectly well happen. It can perfectly easily happen. Perfectly easily happen that, for example, I of X is 0, and then V of I of X is AN. Right. So this will happen, e.g., so let's just do two really silly examples. If I take A1 and I take any infinite set, right, then I ask for I of X. So I of X is a set of polynomials having infinitely many roots. So that's consists of the 0 polynomial. Right? And so then this is certainly 0. Right? Or you can do the same thing. You don't have to, it doesn't have to be quite this silly. I can do something like this. Right? I could do, for example, you know, let me write down the curve if I can. Y equals exponential of X. Right? So that's a curve that looks sort of something like this. Right? And so then if I take, so this is X, the graph of exponential. Right? And then if you go back to I of X, what's I of X? So I of X is the set of polynomial relations holding between Y and X. Right? And X is a transcendental function, so there just aren't any algebraic relations. Right? So if I do this, then again, I of X is 0. It's a set of polynomial relations holding between this X and this Y, which is the exponential of X. So exponential of X is a transcendental function, and so there are no relations. Yeah? And so in this case, in both of these cases, I start off with some set X, you know, which is a set, it's not an algebraic variety. On the other hand, it's a perfectly nice set that lots of mathematicians might want to consider. And you do this I of X, and, you know, and then you do V back, and you get something much bigger than you started with. So, so you don't expect to get an inverse always without condition. So, or here's another case, another example. So, if I write down, as you know, in R2, write down y squared equals x squared plus a squared. Right, then I get this. Then I get this picture. Whoops. Then I get this picture. Like this. Yes? So I just get the hyperbola. Hyperbola. And the hyperbola has these asymptotic lines and so on. I'm just trying to check that I drew it almost correctly. So have I done it exactly wrong? When x is a little bit, oh bother, I think it's that. Yeah, okay. Okay, this is good. So this is x equals a, and this is x equals minus a. Right. So what happens if I do y squared? If I take x to be the set, the set y squared equals x squared minus a, and x positive. Right. In other words, I say, I'm doing some kind of applied maths. I only want to consider that branch of the hyperbola. Forget about that branch. Right? Then when I look at I of x, that's a set of polynomials in x and y that vanish on this half line. So this is the set of polynomials k of x and y, f of x and y, such that f of x, y is 0 on one branch of the hyperbola. Well, these are plane quadrics, plane conics, and plane conics two distinct non-degenerate plane conics can meet in at most 4 points. And so if f of x is identically 0 here, it means it's vanishing not at only 4 points, but at infinitely many points. And that means that f of x of y actually contains also the left-hand side. Then v of I of x in R2 is the whole parabola, hyperbola. Right. So these are just some kind of indications that you can't make these two correspondences. So look, let me just repeat. I did have it written in my notes, but I forgot to say it. When you do this algebraic, you're allowed to write down, this consists of, the conditions here are f of p equals 0. So this is equality. So, for example, if I take the set of points, for example, if I want, if I want f to be equal to 0 and g to be not equal to 0, that's not allowed. This is not allowed as part of Vj. Right? I'm not allowed to say that, and I'm certainly not allowed to say, f equals 0 and g greater than 0 over r. Right? So in this case, if I take this one branch of a hyperbola, then it's not an algebraic set. It's it's maybe a semi-algebraic set, or call it whatever you like, but it's not an algebraic set in the sense of that definition, because any polynomial that vanishes there also vanishes here. So the construction doing v of I of x is the Zariski closure of x. Right? So this is going to turn up. This is going to turn up in other contexts again. And so what this means is, it's an algebraic set, and it contains x, and it's the smallest such. It's the smallest algebraic set containing x. Right? And so, we're getting closer to the place, some of the places I want to go. So you can check that. You can check that if x is an algebraic set, then v of I of x equals x. Right? So another way of saying this is that this is v of I of v of j equals v of j. And this is for all j. Right? And so, I'm not saying anything difficult. I'm only saying here, we know that v of I of x certainly contains x. On the other hand, if x were an algebraic set, then it's defined by some polynomials. It's defined by some ideal of polynomials. And so it's defined, so if, so let me just explain. So I'm sorry, this is very, very formal and, in a certain sense, very boring. So because if v of j, if x is v of j, then I of v of j certainly contains j. Right? And then when I do it forwards, I get the inclusion the other way. So the thing that's going wrong here I write down this counterexample. So here I write down A1 and some infinite set. Right? And then when I do I of x, I find that the ideal of things vanishing on x is much too small. Right? On the other hand, if we knew that x were already an algebraic set, then the ideal of x would already contain those polynomials, would already contain enough polynomials to define x. Okay. So I'm warming up for the Nullstellensatz. So let me just ask as a question, when is it true that I do I of v of j is equal to j? In other words, I take an ideal, so take an ideal j, right? And so I calculate v of j. So this is the set of zeros of j. So j is, in effect, finitely many polynomials. J is an ideal, so it's generated by finitely many polynomials. So this v of j is asking g1, g2 up to gn are all 0. And so this is the common set of zeros of all of those polynomials. Right? And then I want to know that when I do I of v of j, well, that certainly contains j, but I want it to be no bigger. Okay? So when is it true that? So in other words, how can I avoid this getting any bigger? And so there are 3 points. Sorry, let me. So there are, I give these we know these counterexamples. It's not true if the field. Right, that's the main point. And for this, we need K algebraically closed. Right. And then, so we want J to be radical. Okay, so let me explain this. So let's again do an example. So I write down, we have the examples of plane conics that I can work with. So let me write down the equation y equals x squared. Right, and y equals 0. So I write down v of y and y minus x squared. Okay, so v is a set of points. So this is in A2. And what set of points is it? So this is just the point 0, 0. right? This, I have to have y equals 0, so I have to be on the x-axis. At the same time, I have to have y equals x squared, so x squared has to be 0. So x squared has to be 0 is sort of this point with some, mess coming out of it, but it's a set, right? It's a set of, the x is supposed to take values in the field k, and so it's in a field k, I take the set of elements x with x squared equals 0, so that's just 0, right? And so when I do I of v, I of v of this y, of this j, let me call this j, right? Right, what I'm getting is this, the ideal xy. And that's bigger than this ideal. This ideal here is the ideal x squared y. Right, and what's wrong? Well, the thing that's wrong is that this damn fool function here, right, I started off perfectly sensible intersection of two plane conics, right? But actually, if I took a linear combination of these, I would get x squared equals 0. So, if I'm writing down, if I'm trying to define a set, and I write down the condition x squared equals 0, then I'm just doing something silly. I should have written down x equals 0. So, definition, the radical of j, so this is the radical of j. This is the set of f in the ring such that f to the n is in at j for some n. Yes? So j, I start off with an ideal j. I define the radical by this formula. So in this case, the element x, this element x is, it's not in j, but it is in the radical of j, because x squared is in j. So, this is, I'm heading towards the statement of the Nullstellensatz, and you have to have this, you have to make this distinction of the radical before you can get a sensible statement. Okay. So if given a ring A, ideal J, the radical of J is still an ideal of A. Right? And so what do we have to prove? Well, I've got f in J. F in radical of j means that f to the n is in j for some n. So if I take a f to the power of n, this is a to the n times f to the n. So this is in j. And so AF is in the radical. Right? And then if I do, f plus or minus j, f plus or minus g. So suppose f is in the radical, suppose f and g are in the radical of j, then f to the n is in j and g to the m is in j for some m. Right, and then I'm going to write down, for example, I can write down, I don't know, n plus m. I write down f to n plus m minus 1. Right, and then this is f to the power of I, g to the power of j, times some coefficient here, I plus j equals whatever it is, n plus m. It doesn't really matter. Right, and then there's some binomial coefficient here, probably I plus j, choose I or something. I'm just writing out the binomial coefficient, right? But here, this means that I is greater than n or j is greater than or equal to m in every term. Right, and therefore this thing on the right is in j, is in the radical of j. Sorry, this term here is in j. Right, so f plus or minus, so yeah, f plus or minus, yeah. So f plus or minus g is in J. Okay, so so the radical of J is an ideal. So then the Nullstellensatz, let me state it and finish today, because if I start trying to do a proof, I'll be less than convincing. So the Nullstellensatz so this is also called Zero's theorem. I found its proper translation in Korean Wikipedia, so you can easily find it. Just go to Wikipedia and ask for algebraic geometry. You'll get out the same thing. So I'm working with, so there's an assumption here. I'm going to say K is algebraically closed. Right? And so, you know, that we already see the reason for that in these simple examples. If K is not algebraically closed, it will happen quite often that the variety of some sensible so let J in K of x1 up to xn an ideal. So the first part is, you know, is in some ways the hardest thing to prove. The hardest thing to prove is the thing that looks completely trivial. If J is not the whole ring, then V of J is not empty. Okay, so this itself is this is really the main statement. This is called the weak Nullstellensatz. Right. So if J was equal to the whole ring, then when I write down this V of J, I'm including the equation 1 equals 0, and then I get the empty set. Sorry. If J is not the whole ring, then V of J is not the whole. So if J, to say that J is not the whole ring means that what I've got it here is some set, so in other words, Fi is a set of polynomials, and it's not possible, and you know, the Fi is J, is an ideal with J does not contain 1. Right? So I have a set of polynomials, and it's not possible to express 1, the constant function 1, as a linear combination of the FJs. Then the FIs have a non-empty set of roots, so have a common root, have at least one common root. Yes? And so this is a statement, this statement here is about the existence of at least one point in this variety. Right? So, you know, this looks pretty trivial, but, you know, it's going to take a whole lecture to prove, and, you know, if you think it's trivial, you can go away and try and prove it for yourself, and eventually you'll end up looking at one of the textbooks, because it's not trivial. It's not. Right, and then the second part, so this is sort of part 1. Part 2 if I do this, so I ask this question, if j in k of x1 up to xn any ideal, then if I do I of v of j, then I get the radical of j. Right? So that's exactly what happened in the example over there with those two tangent conics. I start off with these two equations, I find their common points of solutions, and then I ask for the ideal of all functions vanishing on them, and I find something here which is the radical of the ideal j. Right? So this second part, you may think the second part is sort of has more content than the first part, but actually it's so 2 is a little corollary of 1. Right? One is the hard statement. So I think I'm going to leave this to next time because it's a sort of big thing to prove. Okay, any problems? So, you know, all of this is just definitions, and, you know, it's all algebra and definitions, and I don't know how to, you know, I mean, you have to, this is not the real substance of algebraic geometry, this is just, you know, doing the hard work to lay some foundations, and then we're going to build interesting structures on top of the foundations. This is okay. So can we remember to bring some white chalk?